Hello, welcome back. Today we're doing number 98, validate binary search tree. So given the root of a binary tree, determine if it is a valid binary search tree, BST. A valid BST is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of the node contains only nodes with keys greater than the node's key. Okay, there's no talk about equality here. Less than, greater than. Both the left and subtrees must also be binary search trees. Okay, so it's a recursive relationship. Example number 1, we have a 2 here. Everything on the left should be smaller. And that's just the number 1. We have a 3 here. Everything on the left should be larger. So let's look at the other example. Close the screenshot. And we have a 5 here. Everything on the left should be smaller. And then on the right we have a 4, and then it goes 3, and then the 3 is smaller than the 4, but it's not larger than the 5, so it means that this tree is invalid. Okay, so this is a perfect example to illustrate, and maybe there's some more illustrative examples as well. So we have a 5, a 1, a 4, a 3. So at this 3, they're saying we should have known that something was wrong. And why is something wrong, right? So from the 5, everything on the left, everything this way and all the way into infinity is smaller than 5, right? So if we're processing some node, we have a function that takes a node that's in this direction, right? That's going left, I guess. Then we should know that the max value is 5. Right? Going this direction. If we're going the other direction, we should know, right, this node, that the min value is 5, right? Nothing could be smaller than this 5, right? So actually this 4 already, I overlooked it. The 4 already breaks that quality, right? 4 is to the right side of 5. It already breaks the quality. Imagine if this was a, let's say 7, right? So 7 is completely valid, especially when the min is 5, right? And 7 could be as large as it wants, right? I guess 7 could be, it could be 1,000, right? It could be 700. It could be 7,000, right? 7,000 would be a completely valid number. And why is that? Well, so at this position, actually, the maximum is infinity, right? And I guess corollary to the other side, the minimum at this point, right, is infinity. But it's not always infinity, right? So what is the bounds, right, of this number, this 3 right here? Let's focus on the 3. What is the bounds of this 3? Well, going from the 7,000 to the 3, it's smaller than the 7,000. That's great, right? But 7,000 is at this node, right? At this function node, 7,000 is its, let's see, everything this way, right, needs to be, it needs to have a max of that, right? So the max is 7,000, right, going this way. And what is its minimum? It can't be 3, right? The minimum should actually be carryover from here, where min is equal to 5, right? So it seems like there's a going left, going right concept here, right? So what happens when you go left? So let's say you take the 5, right? What happens when you go left versus when you go right? So when you go left, the maximum becomes this node, right? The minimum is infinity. So I guess it starts infinity here, negative infinity is the minimum, and maximum starts at infinity. So when you go left, right, let's say it's a function here, go left, So when you go left, the updated is the maximum. So the max equals this node's value, and then the minimum is unchanged, I guess, right? The minimum is the minimum. Same function. When you go right, what happens? When you go right, this side right here, make this green. When you go right, what's updated is the minimum. You're setting a new floor for minimum, right? So here, 5 is the floor for minimum, right? And when you go left, you're setting a new maximum, right? Here, 7,000 is the floor for maximum. So when you go right, the minimum equals that node, and the maximum is not updated, right? What happens when you reach a leaf? So what happens when you go right on this 3? I guess if you take any node and the node is none, you just return whatever the no op of your function would be, right? You return some no operation. I guess because this is a validation, once you find something that goes against it, we can return false. And then if node is none, no op. Now what's on the other side of this? Can the 7,000 have a 6? It cannot have a 6, right? When the 7,000 goes right, let's look at the positions. When we go right, we are updating minimum, right? So when we go right, that 7,000 is the minimum, and 6 is obviously smaller than 7,000. If this was a 6 million, we'd be completely fine, because the maximum always going right, infinity has never changed, right? So we just need to think towards what are the conditions going left and going right. And when we go left, when we go left, the maximum is updated. When we go right, the minimum is updated. Right, that's the bounds of this, right? So 5 here, infinity is the bounds. When we go right again, it's updated to, I'm going to go ahead and I'm not sure how to use layers, but maybe if I added a new layer here, it'd be helpful. Okay, so I'm in a new layer. I'll make this red. So at this point, this is 5 to infinity, right? That's the bounds here. Now what's the bounds here at the 6? Well, this is actually 6,000. This is actually 7,000 to infinity, right? Because we get the 7,000, we set it here, we give it the bounds for this condition. This is 7,000 to infinity. Going the other way, this was 5 to negative infinity, right? We get it from here, and we set it to this 1. The 1's bounds is maximum 5 and negative infinity, right? What happens on this 3, right? This 3, instead of this 5 here, right? We're at the 7,000, right? We're here at the 7,000. And 7,000 is the new max, right? And the bounds here actually goes to 5. This needs to be between 7,000 and 5. This 3 does, right? Kind of messy, but hopefully that illustrates the point. So let's look at the code and let's look at how we can implement what we just drew here. Okay, so a valid BST, we're given a root, right? And we want to traverse this tree. As a template, I like to do this, where a go function takes a node, and we pass in this root here, right? And if you want to just test it, we can print the value, and we could print the value here, and we could see the root, right? So the root here would be 5, right? So this case 2 is this one right here, right? So the root here is 5. Now, what are the bounds for that 5? Well, when it's a root, there are no bounds. The root can be any value. So maybe we can put the go value, or the go can have arguments, minimum value and maximum value. And in the beginning, the minimum value is, there is no minimum value, right? So it's float negative infinity, and then the maximum is float infinity, right? So if the no.value is smaller than the min value, or the no.value is larger than the max value, then this go function should return false, right? And I guess we can say if should it return false or true? Let's think about it. Maybe it could return true. We can say find violation, right? And then if go returns true, then this function returns false, right? Sorry, that's not called go anymore. Find violation returns false. Okay, perfect. And what that lets us handle is if that value is none, right? We still want that leaf case. Then there's no, we could just return none. Or return false, doesn't matter. Okay, so we have to go left. We have to go right. And let's remind ourselves, what does going left mean? Going left means we're taking some position here, and we're updating that as the new maximum. So going left, just put here, is the new maximum. All right, so go left means I'm going to find a violation of this new node, node.left, right? And min is still min, so min value is unchanged, but maximum is now node.value, right? I see. I don't think I can use the return values out of here because I want to both go left. Yeah, I don't actually need the return values. I guess what I could have done is, let's think. Do we want to use the return values? So if we do, we want to coalesce these operations. We want to coalesce go left, go right. So if we find a violation here on go left, then that's going to return true. Okay, I guess if we want, let's write this out. If we want, we can return the combination of these. So we can return this violation or that violation. This might make it really hard to read. Found left, found right, found left, or found right. Okay. Yeah, we don't want to print it if it's none. And it wouldn't be val that's none. It would actually be the node, right? So we're getting a node. All right, let's submit this and see if we got what we wanted. Aha! So in the beginning, when we were reading the problem, I didn't know what to do if it was equal, but it looks like if it's equal, then that's a violation, right? So it has to be so I guess we can rewrite this to make this prettier, but we could also just check for equality. This isn't the prettiest way to do it. If node.value equals min value or node.value equals max value, that returns true. We did find a violation there. All right, so I hope that was helpful. We basically have exactly what we have in the diagram, where when we're going a certain direction, we update one of the parameters, a minimum value or a maximum value. And if we go into the other direction, we update that. Improvements may be on readability. We have a lot of return trues or a lot of return falses. It's finding a violation here. We can think through maybe a better way to do that. I guess I could have just made this equal sign. I guess I didn't really need to write that code. So that's also I guess that was also unnecessary. I wonder if this improves time. It's probably too small of an operation to test, but we were 37 before, 41 now, even though we got rid of an operation. So these numbers aren't always exact, especially when they're so close. There's probably a way to improve the speed here. We don't need to call both of these. The second we find a violation, we can just end all operations, right? I mean, it's a micro optimization. If we found it on left, right? We can actually just return true. And then if found on the right, return true, return false otherwise. So we had 37, 41, 38. Not much of an optimization. All right, so hopefully you understand the general idea of it. Is that we're updating some parameters as we're moving through the tree. Those parameters create the bounds of what is acceptable values. And once you figure that out, you got the answer to the problem. Thanks again. It's been fun. Leave comments on which questions you want me to tackle next. So far, I'm going through the grind 75 problem by problem. So, this problem is the next one I'm checking off. Validate binary search tree. I got number of islands left. Rotting oranges. That finishes week 4. See you on the next one.